Okay, so let's speak about BFS or breadth first search. So BFS is yet another variant of graph search where we use a queue instead of using a stack. If we use a stack, we get DFS. And generally speaking, DFS is good for investigating and understanding the structure of the graph, while BFS is good for computing distances from a source vertex. Okay, before I go into too deep into the shallow water of BFS, here's a cute comics by XKCD about DFS, or how to randomly explore knowledge, which if you use the internet nowadays, it happens all the time, especially if you go on Wikipedia. You start going around and following links, and you end up learning things you don't want to know, or do want to know, but are not really what you started for. Okay, so a quick reminder of the Q data structure. By the way, let me remind you that in this lecture, like the previous lecture, everything is based on the idea that you already seen this stuff before. So we kind of try to emphasize the more interesting and the deeper things and how to do the analysis, and less on introducing you to those concepts because we assume you already know them. So we quickly go over the basic algorithm, emphasize what we need to emphasize, and move on. Okay, so a queue, a FIFO queue, which is what we will need. The elements enter from one side and leave from the other side. This is called first in, first out. Inserting an element, instead of calling it insert, it's called in queue. Don't ask me why. I'm not in charge of the concepts or the convention on this. And removing it from the queue in the end is dequeue. So it goes. So we're going to essentially take the DFS algorithm and just replace the stack with a queue. Now, of course, when we describe DFS, instead of using a stack, we describe it recursively, but it's straightforward to describe DFS using a stack, and then you will get exactly this code, except that we use, as I said, stack instead of queue. Okay, so this is the standard BFS from a vertex. We mark all vertices as unvisited, right? Then we initialize the search tree that we are going to compute to be empty. We set the first vertex, we mark it as visited, and we enter it to the queue. And now we start. And now, as long as the queue is not empty, we remove an element from the queue, and for each adjacent edge to it, we visit its vertex. If it's not visited, we mark it as visited, and we add the edge UV to the BFS tree. And that's the algorithm. Right? Pretty simple. Okay, as far as running time, every vertex is going to be visited once, and it's easy to verify that every edge in the graph is going to be inspected twice in this stage, right? So, sorry, in the loop here, every edge is going to be inspected twice by the two endpoints. So it follows that the running time is proportional to the number of vertices and the edges in the graph, which is n plus m. Again, I remind you that the convention is that n is the number of vertices and m is the number of edges. Okay, let's see an example. So in the beginning, we start with vertex 1, and it's the only vertex in the queue. And the algorithm dequeue it, and it visits two neighbor 2 and 3, which are unvisited. So it marked them as visited and add the edges 1, 2, and 2, 3 to the tree. And now the queue is 2, 3. Okay. Now it's going to visit vertex 2, right? Because it's the head of the queue. And when it visits the vertex 2, it's going to visit all the neighbors, so 1, 3, 4, and 5, right? The edge between 2 and 3 is an edge that connects the vertex already visited, so this is the so-called cross edge. And the new queue after we handle 2 is going to be 3, 4, 5, right? And we continue in this fashion. We go and we visit 3. 3 is connected to 1, 2, 5, 7, and 8, right? So this is going to be a back edge. I didn't even mark it in the graph. And 7 and 8 are added to the queue, right? Next we handle vertex 4, but handling vertex 4 has nothing interesting to say. You just empty the queue. Then we handle vertex 5. Then we handle vertex 7, right? 8. And finally we handle vertex 6. And now the queue is empty and we are done. Okay, that was a bit hand-wavy, but hopefully you understand the idea, right? So it's a very simple algorithm and yet very powerful. Okay. Let's see an example of this algorithm using directed graph, and this time I would have to do it by hand. So maybe more interesting. So initially the queue is A, so we go to A. Hello A, happy to meet you. And from A we look on all the outgoing edges, right? So it's B, C, F, right? So we add B, C, F to the queue. This is the queue at this stage. And we add those edges to the tree being computed. Okay, now we go to the head of the queue, it's B. So we delete it, we dequeue it, and now we are handling B. B has an edge coming out of it at E. That's the only outgoing edges, so the queue is going to be C, F, E, right? Now with the queue C and we handle C, so the queue is F, E, and let's handle C. C has one outgoing edge is D. C, E, F, D, right? So we add this edge to the, right? We add this edge to the tree being computed, and we added D. Now we handle F. We take F. F has an edge going to B, but that's a back edge because B is already visited. So B has only one outgoing edge, which is new, which is G, right? So E, D, G. Okay, and we have, of course, this edge, the edge of the computed tree. Next, we handle E. E, add the edge to H, right? All the other edges are already there. So we get the Q is going to be D, G, H. Now we handle D. Right, just a second, I have to add this edge to this tree, right? Because when we handle D. Okay, now we handle D. D has nothing new to add because in fact we visited all the vertices. So the Q is going to be GH. Then it's going to be H. And then the Q is going to be empty and the algorithm finishes. Okay, so this is the algorithm execution for example for directed graph. Okay.